Ever wondered how scientists automatically, identify earthquakes? It's not magic, but it's pretty close. Today we're talking about a fascinating paper that benchmarks different AI methods for earthquake detection.
It's all about speed and accuracy. Finding those crucial P&S waves quickly is key for early warning systems.
Exactly. This paper uses a massive data set from China, millions of seismic recordings. Wow.
That's right, the DI-10 dataset is huge, and it lets them compare different AI models fairly.
So which AI came out on top? Let's find out. So the paper looks at 7 different neural networks, right? All trying to pick out those seismic waves.
Yep, a mix of popular architectures. We've got UNet, UNet++, RNNs, EQ Transformer, and even some lightweight networks they call LPPNs.
And they're all doing the same job, just using different approaches?
Precisely. Some use convolutional layers, others recurrent ones, and some combine them. It's like comparing different tools for the same task, right? This DI-10 dataset, it's massive, you said? How do they use it?
They split it into training and testing sets. The models learned from the training data and then were tested on unseen data to see how well they generalized.
So, like a real-world test?
Exactly. And they used a clever labeling scheme to train the models. They didn't just mark the exact arrival time, but created a probability window around it. Smart.
So how do they measure how well these AI models performed?
They use standard metrics like precision, recall, and the F1 score. Higher scores mean better performance. They also looked at the timing accuracy, how close the AI picks were to the manual picks.
And the results? Did one AI clearly win?
The RNN and EQ transformer models performed best overall, likely because of their ability to consider a wider context in the seismic data. Makes sense.
But speed matters too, right? Especially for real-time earthquake warnings?
Absolutely. They tested the models on both CPOs and GPOs. The LPPNs were surprisingly efficient, especially on GPOs.
So a trade-off between accuracy and speed?
Exactly. The RNN and EQ transformer were more accurate but slower. The LPPNs were faster but slightly less accurate. It depends on your priorities. I see.
Did any of these AI models make mistakes, like false alarms or missed earthquakes?
Of course. They analyzed false positives, incorrect picks, and false negatives, missed picks. The rate of these errors depended on the model and the signal-to-noise ratio of the seismic data.
So noisy data makes it harder for the AI?
Precisely. Low signal-to-noise ratios led to more errors. But even with noisy data, the AI models still outperformed traditional methods. Impressive.
The paper also mentioned something about sampling rates. What's that all about?
The seismic data can be sampled at different rates, like 50 hertz or 100 hertz. They trained models on both and tested them on the other. Performance was best when the training and testing rates matched.
Makes sense. If you train on high-resolution data, you might not do as well on lower-resolution data.
Exactly. It highlights the importance of using training data that matches the type of data you'll be using the model on.
This is great research, but what about accessibility? Can other scientists use these models?
Yes. The authors made all their code and trained models open source. They even included a tutorial to help others get started.
That's fantastic. Encouraging collaboration and further research. The paper also mentions something called ensemble learning. What's that?
They combined the predictions of several models to improve overall accuracy. It's like getting a second opinion. Averaging the results often reduces errors.
So a team effort, even for the AI?
Exactly. The combined model had a lower error rates than any single model. Very cool.
So what are the real-world implications of this research?
Faster and more accurate earthquake detection is crucial for early warning systems. These AI models could significantly improve those systems, potentially saving lives.
And the open source aspect makes it even more impactful.
Absolutely. It allows other researchers to build upon this work and develop even better models.
What are some of the next steps in this area of research?
Further improvements to the models, exploring different architectures and testing them on even larger and more diverse data sets. Also dealing with more complex seismic signals.
So there's still a lot to explore.
Definitely. The field of AI and seismology is rapidly evolving.
Let's recap. This paper compared 7 different AI models for earthquake detection using a massive data set.
The RNN and EQ transformer models showed the best accuracy, while the LPPNs were the most efficient. The choice depends on the specific needs of the application.
And the open source nature of the work makes it a valuable resource for the seismology community. So it sounds like this research is a significant step forward in earthquake detection.
Absolutely. It provides a valuable benchmark for AI models and highlights the potential of these technologies to improve earthquake early warning systems. The open source aspect is also key for future advancements in the field.
That was a great discussion. Thanks for sharing your expertise.